Hello, so today we are going to do this problem from Leetcode challenge. The problem says it's cousins in a binary tree. So the problem says in a binary tree, the root node is at depth 0 and children of each depth k node are at depth k plus 1. So we have a binary tree, root node is at depth 0 and children of each depth k are at depth k plus 1. Two nodes of a binary tree are cousins if they have the same depth. So two nodes are cousins if they have the same depth but have different parents. Okay, so we have two nodes we can say that are cousins if they are at the same level essentially, but they don't have the same parent, right? And we are given the root of a binary tree with unique values. And the values x and y of two different nodes in the tree, and we want to return true if and only if the nodes x and y with values x and y are cousins. Okay, so we have this binary tree, and we have x equals 4, y equal to 3, and so they have the same parents and they are not at the same level. So do the nodes have unique values? Okay, yes, yeah. So with this binary tree, we have 5 and 4 that are at the same level. And they have different parents, sorry. So that means that 4 and 3 have different parents. Like it's only the direct parent that we are looking at here. Okay, so here we have 5 and 4. They have different parents, and so true. Here we have 2 and 3, they have the same parents, so we should return false. They are though at the same level. So each node has a unique value, okay? So let's think about this. So the first thing is, so what do we want to know? So we get our x and y cousins, and the definition of cousins is basically different parent and same level, or same level and different parents. Okay, the data that we have here is the root of the binary tree and then x and y, right? And so let's just dive a little bit deep into the same level here. So same level, I mean, we could compute this using BFS, right? Now for different parents, I mean, in BFS we have access to the parent, right? So I'm thinking just use BFS here. So how can we do BFS? So actually thinking about this more, I think we may be able to get it with BFS. So we can just try to find the node x and y. So how about just DFS find here? And then, so if I do something like this, what I do DFS find here with root for x, right? So let's say I get x node, and then I get x level, okay, using DFS. And then I do the same for y. So what this would mean is that I could just check if I will need to, so here I want to find the parent. So basically, I will need DFS find to return parent and level. So that way, so x parent here, and then x y parent, right? And so if the parent value is equal to, so I could just return this is equal to the parent of y, the value there, and the level is the same. Now, how can I implement DFS find? So it would have, of course, the node and x. So it's recursive, so I will need to do something like maybe node.left here, and then node.right. And I need the parent, I need to pass the parent. So here the parent starts out as none for the root, right? So when you call it initially, it should be none. And then I'll have to pass that, so maybe this here, and then we could have node. And if node.val is equal to x, then at this point I should return. I will need to also keep track of the level. So I will need level here. What this would mean is this would be level +1, level +1. And if the value is equal, I'll just return parent and level. Now, how do I know when to stop with the recursive function? We are guaranteed to find it, right? So it's guaranteed that x is in the binary tree. Okay, so I will need to check here if not node, right? If not node, well, let's just return none maybe, right? So here, if let's say left parent and left level, right? So if not left parent, if left parent, which means we found it, then we could just return that. Return basically left parent and left level. Same thing here maybe, so left right and right parent and right level. I mean, at this point we just have to return this, right? Yep. This may work. I'm not sure about this portion, but so basically, if we find it on the left side, or maybe we reach it. Yep. So yep, if we reach it all the way to the left side and we didn't find it, we should just skip and try the right side. And if we don't find it on the right side, I mean, we should just give up at that point, right? Yep, so I think this should be reasonable, so let's try. So this is the definition here, and we need to and then here this should start with root, and the parent is none, and the level starts out as 0. Same thing here. And this is for the left node, right node. And if it's equal, we just return parent and level. Okay. Okay, so it seems good for that one. Let's try this one. Okay, so this one didn't pass. Just put this one here. Just make sure. So the second one should have returned 5 and 4, should have returned true because it's different parents. Yep, so my problem here, it should be different parents, but the same level, yep. Okay, so that looks good. Let's try to submit to this. There's a problem with this here. With this test case. Is it because the element is not there? Well, it's the root. It may be the root. The element may be the root here. So this one, the root, and this one is 3. But the problem is the root doesn't have a... Okay, so yeah, let me try to separate this to make it clear. So it's different parent. Different parent. So let's call this has. And then, or maybe has. So either this or actually we could just maybe get away with not checking the value but just checking the references, right? So different than y parent. That way we could handle the none case. Okay, this looks good. Try again. Okay, so that's accepted. Yep, so it's just about finding the parent and the level for x and y and just checking exactly what the problem asks. Yeah, I think this is using DFS here to find each node. I think this is good enough. Yeah, cool.